Okay, this is the quiz. Don't expect everybody to get every part of it, although I wouldn't be surprised if somebody did. Okay. But we're using this both as a quiz to see what you know about energy. And is a stepping off point into chapter 8, which is on conservation of energy, goes for deeper into potential energy and so forth. Although we've talked about potential energy, problems involving potential energy. We've done labs that involve potential energy and the analysis of the lab, which I haven't had a chance to look at, and I think most have submitted it. Got back yesterday about 5 o'clock. Had to spend pretty much the rest of the day catching up with other courses, and not all of it was turned in because it was all just due on midnight. I haven't had a chance since then. Okay, so I'll be taking a look at that and maybe addressing a little bit of that next time. But you should understand this in terms of the lab that we've done for the most part. The whole thing about the potential energy of the spring, we've talked about it. Don't expect you necessarily to have it mastered yet, but hopefully you do. So here's a situation. It's just like what we've done in lab, except with bigger masses. Got a 5 kilogram mass that's descending. Okay. And it descends 2 meters. I was a little worried. I didn't remember whether I'd written that in or not, but it descends 2 meters and compresses a spring. Now, friction does 10 joules of work opposed to the motion. The spring compresses 6 centimeters. So you can imagine that. You imagine there's a coiled up spring on the floor. This thing descends. And you got 2 20 kilogram masses on a light beam, each 3/4 of a meter from the axis, 75 centimeters, 0.75 meters. Make sure you see that decimal point. You could do it for 75 meters, but the numbers are getting nasty. I mean, lots of zeros and stuff. Okay. So what's the maximum speed of these masses? And what's the potential energy of the compressed spring? Then I'll have a couple of other questions involving motion. But those questions are going to be easy. Just want to do that to be sure you review that, because I think next week the midterm exam will be in the testing center. Deadline of 2 weeks from tomorrow, I think. Okay. So we want to both look at the new chapter and do a little bit of review to make sure that you're equipped. Okay, so see what you can do with this. Okay, as I just said, if everybody had put their heads together in this, I think y'all would have done it, but let's just see. First, most obvious thing. 5 kilograms descends 2 meters. Calculate the change in potential energy, or calculate the work done by gravity, right? So I'm going to say, well, the obvious thing here is gravity does 50 newtons times 2 meters, 100 joules. This thing's descending, so the direction of the gravitational force is downward. The direction of motion is downward. Now, I said 50 newtons times 2 meters because I know that the two forces are in the same direction and it's going to be positive, right? To be really careful about it, you might want to write that as negative 50 newtons times negative 2 meters. thinking of upward as the positive direction. Sometimes it's okay to think of downward. If everything's going downward, you could say your y-axis is pointing downward. Do that if you want. But I'm going to stay with the convention that your textbook kind of does, and where upward is usually positive. Okay? So, you get the work done by gravity. We'll just note immediately you've calculated the work done by gravity. Gravity is the only conservative force that acts before the thing hits the spring. Okay. After the thing hits the spring is conservative. We assume the spring is exerting a conservative force unless we say otherwise. Okay. And pretty much everywhere in this course, we're going to be dealing with ideal springs, at least till we get to the lab, and then we measure how not ideal they are. Okay. So there we have quite a bit already. Now, friction. Friction and gravity do network. Do 100 joules minus 10 joules, which is 90 joules. This work is opposed to the motion, so you know that it's going to be in the direction opposite the work done by gravity. Now you could also calculate that, okay, except they didn't give you the force. Now some people wanted to figure out the frictional force. Okay, we'll do that, but it's totally unnecessary. We know how much work it does, and that's all we really need to know to answer all these questions. But it's good to know that you could calculate the frictional force. If it goes 2 meters and friction does 10 joules, okay, you got a frictional force of 10 joules over -2 meters, which is -5. I'm sorry. It's -10 joules over -2 meters, which is 5 newtons upward. Okay. You know it's upward because it's in the direction opposite motion. You know the work is opposite motion, so you know that's -10 joules if the gravity does 100 joules, right? So there are all kinds of ways you can figure out the signs and everything. But the frictional force is 5 newtons upward in case you need that for something, which you don't, because I didn't ask about it, but maybe I would. I could easily surrender. Well, what was the average frictional force? Okay, so you got to know how to calculate that. I didn't ask for everything, and some things are kind of incidental to the problem, so I'll talk about them, but I'm not going to write too much on the board, so you can kind of take a note. Yeah, we can find the frictional force. That's really easy, because we know how much work and how far. Okay. Now, it gets a little trickier. These two 10-kilogram masses are at 0.75 meters from the axis. And we want the maximum speed of these masses. Well, by the way, I'll say the maximum kinetic energy of the two 20-kilogram masses happens at the instant the spring is encountered. Okay. So we still don't need to calculate anything at all regarding the spring to answer this question. in this question. And then we get into spring potential energy, because that's something I think you might be a little less familiar with in working kinetic energy, okay? I better write that a little more clearly, although it's written so beautifully. I hate to do anything less beautiful. I'm going to write 1/2 the total mass. That's important to understand, important to remind yourself, okay? Times V max squared. And I call it V max. So now you can, I mean, that's what it has to be. If you're going to use 1/2 mv squared, you want to be specific about what mass and what velocity you're talking about. We're talking about the total mass because you have 5 kilograms of mass moving and you have 40 kilograms of mass rotating. Okay. And even this isn't quite correct. So I'm going to change a little something. I'm going to say it's the sum of 1/2 mv max squared. Why do I say that? Because the 20 kilogram masses are going to be rotating about an axis where the 5 kilogram mass is moving downward. You know from experience that the masses on that beam will tend to move a whole lot faster than that descending mass. That descending mass moves very slowly. If you've got more mass on the beam than you've got descending, especially if it's a long beam. So that should be something you've thought about in analyzing parts of the lab. Okay, that's something you should be able to relate to, even though if you didn't think of it right now. So you'll think of it next time. Well, so that is kind of obvious if you're used to the system, but not totally obvious when you're trying to sort all this out. Kind of tend to forget about that. Okay, how do we read these boards? I don't think I'm gonna have room on that. Do this. And see how much board I've got over here. Okay, I'm going up to the edge so I can pull it back a little bit more. Still good. Get as much as I can. Okay, I think we're okay. All right. So we've got something here that we don't know. We don't know what the ratio of the speed of this 5 kilogram mass is to the speed of these 20 kilogram masses. And that depends on the length of the beam that supports these 20 kilogram masses. Now we're assuming the beam has no significant mass. or significant moment of inertia, but we haven't talked about that except just vaguely. So if the pulley on the beam let's say it has a radius of 10 centimeters. That gives it a pretty big diameter, almost the diameter of my hand span. So that'd be a fairly big pulley. Then what? The ratio of the speeds of the 20 kilogram mass is B to the 5 kilogram mass. This gets into the geometry of a circle and a few simple relationships that you know, but going to give you a minute to think about that and see if you can put that together. Okay, I think I find that it's not obvious what that ratio ought to be or how you would even reason it out. Okay. Here's your reasoning. One revolution of the pole equals one revolution of the beam, right? The beam has a radius 7.5 times the pulley's radius. 10 centimeters, 75 centimeters, right? And of course, you got to work that out. I started to write that out backwards. I apologize. How do we start to write that? I like the way I wrote it now and lost it, but
Growing through your public spaces.
I'll say speed of the beam is 7 times 5 times the speed of the point on the pulley's rim, right? Now the question is, how is any of that related to the speed of the descending mass? Okay, imagine that this is your pulley. It's rotating, say like this. And the spring is wrapped around this thing maybe several times, but then it comes off in this direction at this point. Okay? Say you make a mark on the string right here. How fast is that mark moving? It's moving at the same speed the rim of the pulley is moving, right? Because it's moving right along with the rim of the pulley. Now, when it comes off, it doesn't change speed. That mark on the string keeps moving along at the same speed as the rim of the pulley. Does that make sense? Make sure you understand that picture. Make sure you understand. Think of a mark on the string and how it's moving before and after it comes off of the pulley. Okay, so now we've established that the spring is moving at the same speed as the rim of the pulley. So how fast is that mass descending? The same speed as the spring. Okay? That makes sense? So the speed of the spring I'll say unraveling because I can't think of a better word. Put it in parentheses because it's not really the right word. And are there two L's in unraveling? I kind of think maybe, so I'll fudge it. Speed of the unraveling string equals the speed of the rim which is equal to the speed of our descending mass. I don't have room to write the word descending, so I'll say our 5 kilogram mass because we know that's what's descending. So why are we doing this? I'll remind us again. I don't want to I'll use M rot, M sub ROT for rotation. B max rot squared. And I use DESC for descending mass times and that equals what? That equals your total kinetic energy, which is what? 90 joules, it's 100 joules the gravity is done on the mass minus the 10 joules that friction is done to oppose its descent. Make sense? So we know what number we're going to put here, but I'm just going to do it with symbols first, so we see that we have to calculate the kinetic energy of the rotating mass based on its speed and the kinetic energy of the descending mass based on its speed. Now, we know here to put a max in there. V max descending. So 1/2 of the mass of the rotating part of the system times I can write the whole thing in terms of the velocity of the descending mass. And it's very simple. This ratio is simply the radius of the path of the rotating masses divided by the radius of the pulley. It's attached to the beam. And that ratio will change depending on the radius of the pulley. Now, a little bit of information on the system that we're using. We have 2 pulleys. I think I can pick this up without. Okay. If you look, I think we got reasonable focus at this distance. There's a pulley right here. Okay. And a pulley right here. This one has a diameter of 5 centimeters. This one has a diameter of 10 centimeters. And as you know, this beam has a radius of 30 centimeters. Okay, diameter of 60 centimeters. Okay. The pulley that we're talking about has twice the radius of the pulley on the system you're familiar with. Now, what in the world did I do with my chalk? Okay. Well, that is something you can easily solve for Vmax descending, right? So you got so we can easily solve this equation for Vmax descending. I don't want to put numbers into this yet. The only number I have is the ratio 7.5. And I could even call that R. And I'm going to do that. I don't like R but I don't really have a good alternative. I'm gonna go back totally to symbols. I wrote this information, but doing the whole thing symbolically. R is gonna be 7.5, but if we happen to have a different pulley, it'll be some different ratio. If we have the masses at a different distance from the center, it'll be a different ratio, right? I could use three symbols. I could abbreviate ratio RAT, wrap, okay? I don't like R because it would be confused with radius. I don't have a great, actually, this is a little better. I'm gonna use rho. Or letters stands for, or it has a lot of other connotations, for example, density. Okay, and a number of others. But I'm gonna just use rho there. And understand that rho is our 7.5 in this case. Okay. Well, if I solve this, I get this. I could write all this out. I write the square as rho squared V max descending squared. Here I just have a V max descending squared. And then I factor out V max descending squared. And the other factor is this, and I divide that into the kinetic energy. I do this because you want to start or continue writing things out in symbols so you think about the relationships. It's also not a bad idea to write them out with the units and solve that way. You want to understand it both ways. In this case, you're 90 joules. Uh-oh. I wrote this down wrong because we don't have equal masses out there. Let's try to make it a little more compact. When I factor this out, I get mass of the rotating times rho squared, mass of the descending just times 1/2 m. And it's 1/2 the descending mass. So when I write this out now, it makes more sense. And I've done a couple of simplifications there. factored in the 1/2, I've got 40 kilograms rotating, half of that is 20 kilograms. I've got 5 kilograms descending, half of that is 5/2 kilogram. And then you work out the numbers. And it turns out 7.5 squared is about 54, 55, say 55. Times 20 kilograms gives you about 1,100 kilograms. 5/2 kilogram. Still comes out about 1,100 kilograms. This doesn't amount to a hill of beans compared to this, for this particular system, or for any of the systems you use in the lab. But you want to write it out because sometimes it matters. Like when you did the Atwood machine, the additional mass that you added made the thing go really fast. Okay. Put a concrete block on the pulley there, thing would descend really well, the whole thing would break apart. You understand, if it was strong enough, that thing could get its rotation really fast. And now you can solve that. And you're going to have like 9/10, I'd say 0.09, so it's going to be about .3 meters per second. Then you can ask the question, okay, how fast are those things rotating? Well, 7.5 times that, okay, comes out between 3 and 4, about 2.5 meters per second. So they're rotating pretty fast. That's how fast the 5 kilogram mass is moving downward at the end. If I did the calculations right in my head, and I think they're fairly right. So what about that spring? Well, everything we've done here just involves conservation of kinetic energy, work energy theorem. We don't need any potential energy, although we did mention it. Kinetic energy is the work done by the net force. Gravity did 100 newtons, 100 joules. Friction did -10 joules. That's where the 90 joules came from. Okay, let's think about the spring. And before I go on to that, let me emphasize the pictures can be very helpful. A picture of the pulley and the beam would have made it more likely that you understand that ratio of speeds than the lack of a picture of a pulley and a beam. Okay, a lot of you draw the beam with a couple of weights on the end. That was good. Okay, because it invokes what we did here and what you analyzed when you analyzed the lab. But you didn't worry about that ratio between the pulley and the radius of the pulley and the distance of the mass from the beam, right? From the axis. Okay. So that really simple geometry was a little bit of a hurdle, wasn't it? It didn't immediately occur to you. It took you a while to understand. You're probably still a little tenuous with it. Make sure you understand it, because when we get to the kinematics of rotation and the dynamics of rotation, you're going to wish you had. Okay. Said many years ago that the difference between somebody who came into University of Physics with a good high school physics course and somebody who hadn't pops up at the instant you hit rotational dynamics. Trying to work that into everything we do, so it won't be such a shock. And I think if you understand everything we've done, it won't be. There's some simple relationships that are pretty obvious if you think about circles and stuff like that. Okay. Okay, well, that's the madness behind my method. Let's hope it works. Okay. Okay, so what about the spring? Well, now I'm going to start talking about potential energy because we've already introduced it. And some of you wrote the definition down in your paper, which I liked a lot. It's equal and opposite to the work done by the conservative force. Just to review, your force you apply to the spring is equal and opposite to the force exerted by the spring. That's Newton's third law. Force exerted by the spring is negative K times, however far you extend it. So that if we just take a specific X, like X equals capital A, and that kind of stands for the amplitude, the maximum extension, the maximum stretch of the spring. We can make this explicit. What we have here is F equals KA. So that the midpoint down here is F equals 1/2 KA. So the area under this triangle, which is your average force times your change in X. You know, I'll use an F bar there. Well, delta X is from 0 to A, so delta X is A. Your average force is 1/2 of KA. The work is 1/2 KA squared. Now, we did that before. I've written that out, talked about it. Hopefully you've reviewed it, so it's not a surprise or a shock. It's pretty simple. Alternatively, the work of the applied force you just integrate the force with respect to position. And I commented, at least one of you, make sure you put that dx in there. Because the next chapter is on momentum, and we integrate the force with respect to time, not position. That gives us momentum, not energy. Big difference, and you want to start distinguishing that now because people confuse the two like crazy. This is the integral with respect to X. There's also an integral with respect to time, and that's something different called momentum. Impulse. Impulse and momentum are interchangeable in both situations. And it's not the integral 1/2 kx squared. But anyhow, that integral is 1/2 ka squared. So this is equal to the negative of this. Okay, this is your conservative force. Your conservative force exerts force negative kx. The equal and opposite force is this one, the force you would have to apply to stretch this thing out. And that work is positive. So that the change in potential energy from 0 to A is positive.
Yeah.
Sort that out, make sure you understand the sign of the work. Okay, well, now I don't think we've got a lot of time, so I gotta see how fast I write this out real fast. I'll just close with this. If you gotta go. That'd take me about 1 minute. What's the work done by the spring? Well, the spring is pushing up. This 5 kilograms is pushing down. So the work done by the spring is well, I don't want to say that. Work by the spring is negative, and it's going to be negative 90 joules. And that's going to be 1/2 Ka squared, where A is the 6 centimeter maximum compression of the spring. You could say it's times negative 6 centimeters, because the spring position changes by negative 6 centimeters. That is the part of the spring in contact, top of the spring. But when you square negative 6 centimeters, you get a positive. So it doesn't matter whether you're compressing or stretching. The work to compress a spring, the distance is the same as the work to extend it through that distance, as long as the spring is behaving like an ideal spring. We haven't squashed the actual metal, okay, or exceeded the elastic limit by permanently stretching the string. Okay, so that's really the answer to that, and we'll continue with that. There's 6 problems in the assignment for next time. I picked out 6 pretty straightforward problems that are much easier than the one we just looked at. Just to get your feet wet, and then there'll be more for Monday.